Today, we're going to talk a lot about network graphs with a big focus on visualizing them. We're also going to be talking a lot about people and what they look like in data and how to make some data for people. Because it turns out I can't take the data from work and just show it to you for some reason. But there's a lot of ways to get around that and still get some really interesting data. I think that's a nice little cherry on top for the session. Great. So starting off, if you want to follow along, there's notebooks. You can make a code space. You can run the code along with us, build out all the things we're building and learn a bit along the way. So included in the resources on the link on the side here is this homepage for the tutorial. So it's building an interactive network graph to understand communities. And there's some info on like what we're doing, links to the different pieces and the different libraries that we're going to use. All this is really just hosted in GitHub. So if you want to go to GitHub, you can see all the stuff here. And you'll see we'll start with like part 0 and work through. And there's like little workbooks here as well as READMEs. And if you're sort of new to this, there's a couple ways to easily get started. One, I think there's a link here. You can click Launch in Binder. This will spin up in a Jupyter instance, Jupyter Hub instance in Binder and install all of the requirements to run this. If you don't like that, you can also run in a code space. So you can click a button here or come up here to code and like make a new code space in GitHub, which will spin up some compute for you dynamically, load all the requirements, and then either launch with code spaces. It's like either VS Code or you can do a Jupyter space as well, and then it'll launch up a little version of that for you. Great way to get started without having to talk about it for more than like 30 seconds or a minute, however long I've been ranting about this. Awesome. So that's the code. That's the main topic. And to start off, I want to show you a little bit of like a problem statement, a couple slides, and then we'll go through some of the tutorial and start building out this thing. But wanted to motivate it a bit with like a why, like why we're doing this. Okay, great. So understanding people with network graphs in Python. We're going to talk about a couple different things. First of all, who am I? Why am I talking to you? So my name's Lucas Durand. My pronouns are he, him, and his. My background is I was once a theoretical physicist, really focused in the computational side of that. So did a little bit of work with Python and a couple other languages, mostly simulating systems and then solving differential equations numerically. After that, I was looking for a little bit of a change, and I ended up joining this company, TD Securities, which is a Toronto-based but global investment banking, wholesale banking operation, and worked as a quantitative developer, mostly doing what I was doing as a physicist, but now with finance instead of with dark matter particles. It was almost as cool. And more recently, also with TD Securities, I've been standing up our data science practice with really a technology and software engineering lens. So really a big focus on like how do we build tools that are available to people, easy to use, and really celebrate, especially Python, to do data workflows. It might be a shocker, but things like Python aren't super popular in banks and in a lot of the like more legacy-driven organizations. So it's been a really fun time over the last couple of years trying to bring that and change that. As you can see in this picture here, my instrument of choice is the saxophone. Love music, and Python is definitely language of choice. I will begrudgingly use other languages, but Python is really the one for me. And here's a fun photo from an in-person Python con a couple years ago. Fun. Okay, so this is me. Hopefully you didn't immediately drop off the call after seeing that. So what's the problem statement? So something that might be similar to you if you've joined a big company or even just like a moderately not well-managed company is it's hard to find people, know what people are working on, and build a network with people. And really building people and networks is really key to success. So struggling to do that from the start, it can be a tough way to start. So problem statement is like, where are my people? Who are similar to me at my very big company? So it might be my first day and I want to find other people who probably know Python, maybe who are working on projects that I'm working on, but it's my first day, so I don't really know what I'm working on. But maybe have similar backgrounds in terms of education, maybe, or interests, other things that we can specify, or just in similar parts of their career. They joined at a similar date to me. All those things would be useful to know, but it's usually hard. So typically, if we look at something like a reporting structure, we can get maybe like a localized view. Like I know who my manager is, hopefully. I know who else is on that direct team. And I might know the whole hierarchy up until the CEO, right? But that's not always the most useful. Especially it's hard to find people who are without lots of clicking or navigation, to find people who are just a couple steps away from me. If you think of it as like a big family tree, it's easy to see my direct family, but even cousins are kind of a pain to find in this way without doing some data scraping. Great. But this isn't enough. So there's a couple reasons why an approach like this doesn't answer all the questions that we have. Like we mentioned, same manager, that's really useful. Theoretically, we're working on the same kinds of things, but not always. Another wrinkle is that regional teams can often have different reporting structures. So here we have like an HR reporting structure, but that's not always the same as a project or a team or a capability reporting structure. And so a common thing that I've seen is that people in different countries or just different continents or different time zones will have different reporting structures. And someone on my team working on the same project, just because they may be in like double. Is that they might be 10 or so steps away from me, going all the way up into the CEO and then back down through another reporting structure to find them. That makes it seem like we're not related at all, but we are. We work together. Another thing that might happen is you might have your team structure not in terms of HR reporting. You might have it in terms of job families. Sometimes people call them like agile pods or like this is potentially a more modern way of doing things, but you might be in a situation where you and your family in this reporting structure all have the same job title, but it doesn't mean you're working on the same projects. Potentially the opposite. You could be a pool of people who are like data analysts, all working in different areas. You have the commonality of having potentially similar skill sets, potentially similar kind of day-to-days, but you're missing now that other piece that we were complaining about, but it's valuable as well, right? The last piece to point out is that things like niche roles, especially in the data science and analytics realm, I see this a lot. Niche roles are often embedded and alone on teams. So someone will get like the data scientist from some other group who will come and be embedded in your team for 6 months, build something. But if they're looking at this reporting structure, they're really out to lunch in terms of finding similar people to talk to. They really are working on different kinds of things. Great. Okay, so a couple of the key things we'll use when we're going through this and building graphs in Python and visualizing them. We'll need to know like what are network graphs, right? So a graph itself, it's a math structure. There's objects inside of it, and different combinations of these objects can be related to each other in different ways. So they can be connected. They can be directional. They can be non-directional, right? But really, we can think of these very vaguely as like blobs of data that are connected in some way that we define. The actual blobs of data here are nodes. You could call them like points or vertices. I like nodes, and nodes of attributes. In terms of the representation, in the libraries that we use in Python, they'll have their own like representation as an object. And I think most of the libraries use like C or Rust in order to implement them to be more performant. But you could think of them as like a dictionary or like just a Python object that has attributes, like a class of some sort, right? Finally, there's edges, and these provide the relationships. So edges connect two different nodes together, potentially two of the same node together if you have a self-referencing edge. And like I mentioned, they can be directed or undirected, so they can point in a direction, or they can just connect two things together. So obvious like ways to use pointed edges is like if somebody like verbs something, node verb node is like I report to somebody. By definition, this is directional. They can't report back to me unless we're in a very strange sort of company. But we could easily also have non-directional things, just like being related by some fact, like both attended meeting or both like Python, right? That's potentially an edge. We won't do it that way, but that's some way that you could use it, right? Okay, cool. So we can actually just take all this data, pump it in, and then visualize it. In this case, like this is with some fake data, and we can visualize like a directed graph. We put people as nodes, so every node has like a person's name in it. It also has at least this like who their manager is attribute. We can use that attribute in order to connect the different nodes together. So now edges are this like manages feature. So someone manages somebody everywhere in the graph, all the way up to the top. So already I think this is great. It's better than the sort of static page that we had. We can see more than we could see before. And we can see people that are at the same kind of level in the organization and that are nearer to each other in terms of reporting structure. So it's a lot of this is off screen, but we could see that people like Christopher Johnson reporting to David Chapman here reports to somebody else off screen, and then reporting into them is Amy Todd and Thomas Yang, right? And so these are like cousins in the family tree, and we can see them as being closer by than somebody far away, right? But this is still just the HR reporting. So how do we actually engage those other attributes? There's some great literature on it, and we can look more at it. I promise you we'll make something a little prettier than this when we actually build the code out. But one of the solutions is to engage these attributes and include them in the graph. So before we were drawing our graphs, and the graph is using just the data of someone's name and their reporting structure in order to draw and find their positions when we're visualizing them. What we want to do, or an option to do here, is to add the other attributes in. So here you can kind of see there's people's names, but then there's also like these light blue blobs nodes with languages. So we have TypeScript, Python, Java, JavaScript, right? We've also have some dark blue nodes here, and one of them is UTC, like a time zone. So now we're introducing these, trying to keep them separate with some, node coloring and styling. But we're starting to introduce more data of different kinds and then connecting those. The idea here is that we can take this information of these relationships and then try to calculate like a distance metric or a nearness metric for our nodes, so that we can see that people are closer to each other based on shared interests or shared attributes outside of just the one single attribute, which is their HR reporting, right? Great. So we'll talk a little bit more about that when we get there, but a really simple way to do this is to use built-in functionality of a lot of the network graph libraries, which is to do plotting. And we can plot the library using a force-directed layout. Basically, what this does is we set up all of the nodes in our graph as little balls, and then we connect them with springs, which are the edges, and then we let a physics engine solve this in order to push and pull the nodes away from each other. Pushing nodes like to push away from each other, but springs like to pull them in together. And this allows the graph to settle into an equilibrium point where it has some sort of, well, it's equilibrium point, but it's found some sort of minimum in its optimization. And then it finds a point to settle into. Sometimes it doesn't happen. It's a little funny to look at, but a lot of the time we can find that nice point, and then we'll have similar nodes pulled together by all of the different springs connecting attributes, and dissimilar ones pushed apart by the natural alignment of the graph as we visualize it. So this is what our approach is going to be: a really simple way to find close peers in an organization. And yeah, there's a little link here if you want to jump to it. It's also on the sidebar if you want to look at the sample app and play around with it. But we're going to be building it in the next hour and a bit. Great. Just a note for inspiration, if we zoom way out, it might look a little bit more like this. And really what we're interested in, and like this is a two-dimensional representation, so we're already adding more than 2 dimensions worth of data and then trying to like squish it down to a space, which could be a little bit difficult. But what we can kind of see here, or the takeaway, is like there are clusterings and groupings of nodes that are more prominent. Some of the nodes are very much individuals and outliers, but the little clustering and groups look like prime candidates So draw a circle around and then try to name. Say like, those are the people who know UiPath, Scala, and Python. I bet they're data scientists, right? Or these folks know a lot of JavaScript and Java. Like, I bet they're traditional app developers, right? Full stack developers. Those are the kinds of tasks we can do after we've drawn and created this graph. Great. Awesome. So if you're following along, let's jump into it. So the first thing we wanted to do is we want to work with some actual people data. So a problem is people data is sensitive. We can't just go and have people's data, not for this presentation at least. And there's some ways around that. So what we really want to do is create something that we can use in this tutorial to represent people. There's a couple features of it that we already decided we cared about and that we thought would be useful. So those pieces were we need some like unique identifier. Names are good. We talked about where they are could be useful. So like it could be an office, a location. We talked about maybe like time zone could be useful. If we're thinking of this application as being finding your peers or finding people similar to you on your first day of work, or just, it doesn't have to be the first day of work. So we probably want to find out people with similar interests, similar locations, maybe, but maybe not. We might not want to always have that on. Teams or project focuses, lines of business, probably useful to know if someone's in like sales versus data versus tech versus, I don't know, like office management. I don't know, all interesting things to be able to factor in. We definitely need to have a field which is a manager. So this is how we build the traditional reporting structure. So we still like that. We need to have that connectivity in there. And then we want to know programming languages, maybe like apps they've used over time. Maybe we're interested in their tenure, how long they've been with a company. That could be helpful as well if you're looking for like, this tool could be equally, let's match up two new hires, as it could be, let's find a mentor for somebody, right? Great. Or projects worked on. Great. I think we said all those things. So how do we do this? It turns out there's a few ways to do it. One is to use this great library called Faker. So check out the docs. But the way Faker works is you import the library. You create a fake instance. We need to do this because it's going to store for us some context of things like what values have already been used, the distributions of these things, as well as allow us to customize this if we wanted to, which we will. So out of the box, it has a way to view a number of the built-in options in Faker to build a profile for somebody. So all of these themselves are separate Faker providers that can generate things like usernames or names or like locations and addresses, right? And it puts it all together for us nicely. So this is good. We could generate like 5,000 people like this, stick it into our graph, and then go from there. But out of the box, it looks like there's a lot of variability in the results here. So here we've got like a job of an estate agent, and there's no estate agents in my company that I was thinking of in my brain, like a generic kind of tech company. So like maybe that's an outlier, but I think if we keep running over this, we'll find out that it really is pulling from like a very large corpus of different results. We also have people in giving residences all over the place. We're getting their blood group, which we theoretically could use this, but I feel like that's probably too personal for the kind of information we want. I certainly don't have access to that. But like some things are good, like actual names is useful instead of calling somebody like employee 123, which is not a great name for somebody. I wouldn't name my child that, probably. Great. So what else can Faker do? We're going to get some lift from using this fake object over something like just like creating a list of unique values and sampling it. So one thing we can do is get unique versions of anything. So I'm using the fake instance here, and I'm going to say, I could say rather fake prefix, right? And it'll give me different prefixes for people's names. That's great. And it'll do it forever, right? With equal probability of pulling them, which is neat. But I can also ask it to give me unique versions. And basically, this is sampling with removal. And whenever I pick out one of the values, it's removed from the possible list of values. I can run this, and eventually it'll raise an exception because I've run out of unique values. Now, this is a bad example because lots of people share prefixes. But it takes a lot longer to run out of unique names. And so I think you're with me. Great. So we can go through all the unique ones and eventually run out of them. And in fact, I've used this twice now, and so there's just none left. There are no more unique prefixes because I've used that up in the fake object. We sort of did this part before, but we can go in and generate a couple people and look at them side by side. Please give it a go and see if this makes sense. But we can generate 3 different people here. Maybe just for sake of visibility, we can just look at the different jobs. We kind of went over this, right? We can look at 5 people, 4 people. We got an advertising copywriter, an exercise physiologist, cool, charity fundraiser, engineer, and engineer, mining. Great. Yeah, I think this is a great company. I actually think this is neat. We're like making a magazine, or like printing ads. Exercise is very important to us. One of the co-founders is doing that. Charity, we're fundraising for that, and then like probably this engineer is doing a lot of work in the mining industry to pay the bills. But I think it's great. Right, it's a little bit wonky. We probably want a way to reduce and focus the scope of where we're getting these values from into something that makes more sense for what we're doing. Great. Cool. So Faker provides providers to do this. We can register new ones. We can tweak the ones that already exist. And this is essentially a way to update their API, which we've decided we like. We like being able to use that unique feature. And we like that we just say fake this, fake that, and we generate them. Conceptually, I could see us building a person who's, like dictionary of like, job equals fake job, things like that. And we can build out like, like department equals fake department. So I like that as a structure, and we can build towards that. Someone in the chat likes fake, and I agree. Okay, so one way to do that, very easy way, is to make a dynamic provider. With a dynamic provider, we're defining what the name of it should be. So here we're going to be talking about like potentially people here have different contracts with the company. So they could be full-time, part-time, or a contractor, right? Let's say those are the options. So we're going to make a new entry in Faker for that. And it's quite simple. We create this dynamic provider. We give it the different options that are available. And then we can register it with our instance. We do that here. And now whenever we call fake employment, we get one of these options. That's great. And the way it works is the same as the other providers that we've been using so far, where it has a big list of possible values, and then it's sampling from that, right? But in this case, what we're seeing, I mean, if we did enough of them to be statistically significant, but you have to bear with me a little bit. What we're seeing is that we're getting equal times, full-time, part-time, and contract. And that's not necessarily typical of what we could have in a company. Now, there's a couple ways to like mess around with that. If we wanted to, we could like try to like add more full times in here, but it's not really. So basically, we're like constructing a larger distribution for us to sample from that's weighted towards them, but there's more elegant ways to do that than just like making a really big list saturated with one value or two values. Great. So we get a little more low level with Faker as well. We can dig into base providers. So not just dynamic, which does a lot of the work for you, but we can build on the base provider. So here, it looks pretty similar. We're still like building this employment status is like our provider class here. Here it was just being built by this factory function. And inside of it, we're defining the different statuses we want. And here, I put them in a little dictionary, and it's mapping to a proportion that we want to be the whole, right? I don't think this adds up to 1, but turns out we implemented it not needing that, which is cool. So all we need to do is create this class. It needs to have a function inside of it that returns some value, right? So we are taking care of the generating results ourselves instead of them writing this logic. So here we're saying just return 1 of the choices available. So we're using the built-in random module inside of Fake. So this lets us use these like unique things later. So we're tapping into that as opposed to using like the class itself outside of it. And we're telling it to make some choices from the list that we provided here. And then we're giving it weights for each one. So this is one more step of complexity here. We're saying still we're sampling from this distribution, but we're going to provide the weights for it, right? Great. So then we can add that, and now when we run employment over and over again, it should be a lot more full times. Yeah, and then the part-time contract popped up, full-time. We could also make that really obvious by putting into like a little loop and like pumping out a few of them, and you should see roughly 7 of these were full-time, which is bang on, and then the contract ones filled out, and none of the part-timers showed up, which is statistically very reasonable for this small sample. Fantastic. So we can also do this, and you could imagine we could extend that even further and create more complex relationships between things, including potentially generating more than one field at a time if we want them to be related or dependent on each other, as well as using, if we wanted to, we could like enforce distribution samples, but generally, as we're sampling this with larger and larger populations, it should take care of that itself. Great. So now we can think about what we actually need for our person. We know how to use Faker. We've done a little bit of magic with random choices from lists. So to try and kickstart this, one thing we can do is write down some data classes that we want to fill out. I think this is a neat, not so new, but new feature in Python to really quickly create classes and objects where we can store data in a specific format. So here we're saying this is information we want to generate for every person. We'll have a time zone. So here's an enumeration for a time zone. In this case, there's only 3. So feel free to like add some more in. The format here is we can just add just the name of it and then automatically generate the value for it, because we don't really need that. We only really need the name if we're going to refer to it. This just makes it easier, more convenient in the future as we're writing them down. Then we can have an actual location object. It'll be a city, a time zone, and a country. Probably we could automatically set the time zone piece based on the city and country. Maybe not, though. Maybe that's not a unique combination. So maybe even the 3 aren't a unique combination. Trying to think about some countries who just like love to have the same city everywhere. Okay, so what does our person look like? Our person will have a name. They'll have a date they were hired. It'll be a datetime.date. Great. They'll have a status. So this will be full-time, part-time contract. We could absolutely have like another enum for this or something. We can have some like list of languages they know, manager, team, title, location, right? Great. So now we can go and create a person. This person's employee number 1. I know I promised we'd have real names for people, but this is the exception. And we can have a nice little representation of who they are. This is great. I made a kind of wonky helper function here because we don't always want to have, especially if you're thinking of something like a programming language, somebody shouldn't necessarily only know 1, 2, or 3 programming languages. It probably is different depending on what part of the business they're in or what their job is. Also, probably I don't know, they and not everybody knows 3 programming languages, right? So it could be different. Plus, it's just different across people. At this point, you could be asking, like, why are we guessing what these things are and then trying to construct data that vaguely looks like it? We could probably just write down the different distributions of things that we see and all the relationships and then sample from that. That's definitely an approach we could use. This is another way we can do it. Great. Cool. So we could do the same thing with programming languages that we did above. We have different weights for different languages, and we're going to use this choose a few, and it's going to choose some number of programming languages for somebody between 1 and some number, and between 1 and all of them, and it's going to give lower weights the larger number you get. So we think a lot of people know 1 or 2 or 3. Very few people know all of them, but it's not impossible, right? Cool. So if we wanted to now, we could like get a fake programming languages, and that'll give me like some number. Great. We can do that. Faker is becoming more powerful for us. And now we can make a person with a name, hire date, status, languages. But I'm going to say with team, title, and location, these are probably all related together. So there's a couple ways we can approach that, but one way is just to write everything down. So here we can construct a view of what our company looks like. Here, let's say that there's a couple different kinds of teams in the company. Each of these teams have different job titles inside of them. The different teams are in different offices globally, right? And then I think that's it. So here we have example, DevX has engineers and an AVP, pretty simple. Sales team has associates and VP. And then what is it like? Support has analysts and managers. So like there's some overlap of job titles. And then similarly, different places like this company's in New York, Toronto, Fort Lauderdale, Dublin, London, Seattle. And then different locations have different teams. Basically what we want to do is for every person here, we're going to pick whatever the topmost of these relationships are. So we're going to pick out, what is it, like a team? Do we pick a team first? Oh, no, we pick a city first because only certain teams are in certain cities. So we pick a city, and then from the available teams in the city, we pick a team. And then from the available titles in the team, we pick a title. And we didn't get smart and say like there's only 1 VP per team, but that's something we could do in this function here, this title city team. We can also register this inside the Faker instance if we wanted to. And that would be fun. So here we have someone in London, Great Britain, UTC time zone, and they're a sales associate, right? So this is nice. This is solving the problem we had before with people's like titles not really matching their department and things like that. So this is helpful, and this is going to be making it easier for us to create a person. So now our person, we can update this and say like, let's get the title city team for the person. And then if they're an engineer, we do something. What do we do with this? Maybe nothing. But if you know that someone's technical based on their title, we can start to give them different features. So in this case, I think the idea was they can know more programming languages if they're technical. But maybe we max it out at 1 if you're not technical. Something to make the data look a little more realistic, right? Again, something we can get from sampling real data as well, but we don't have the real data. So great. So we can look at this in a data frame. We can generate like 150 people, and they look like this. They have names, dates, statuses, languages, teams, titles, and location. We're just missing a manager. So we don't know who manages who. So in this case, let's just use something simple and a bit janky in the code. And let's try to pick a manager for everyone who's already in their team and who has an equal or higher rank in terms of the like different roles in the team. So we'll just like find the maximum rank. So we can assign the ranks to different people by doing a little bit of pandas magic here. But with a couple different functions, we can pipe this in and pick out somebody who satisfies these conditions. So we want the rank to be as big as possible, but we'll accept somebody reporting to someone of the same title if someone doesn't exist, because it's quite possible that we generated a whole team with no VPs in them, and what a world that would be. I've thought about it a lot. Last piece is we actually need a CEO, so all of the teams are terminating at some like top person, but they don't report to anyone, so we can just inject one more person. Now we should have then assign everybody who has no manager to this person, and now we should have a complete tree organization, right? Great. Here I just like flattened out the data frame a bit because location was a little bit troublesome later on, and now we split it out into like the individual columns: city, time zone, country. Great. So does this make sense? We certainly did this, and it seemed reasonable at the time. But what does it look like? Great. So we can do a quick little plot here and take a look at, we can cut and paste it a couple different ways. So here we're looking at different facets of the data. So countries are breaking up into chunks of this data frame. So we're seeing lots of folks in the USA, some in Great Britain, some in Canada, some in Ireland, in this case. And then we're also using color to break up the dimensionality into the different teams that they're on. And so we should see teams being localized, right? So in this case, like if we just look at the business team, they're in the USA, Great Britain, Canada, but not in Ireland. I think that was by our design. Similarly, if we looked at like just the DevOps team, they're only in Ireland. Interesting. I thought that they were allowed to be in Fort Lauderdale or something. It was a long time ago that we were doing that. And then we can start to also see distributions of the roles in different teams. So if we looked at, in DevOps, there's like a kind of flat distribution of engineer, senior engineer, manager. There's not a lot of them to really make this assumption. There's a lot of senior managers, though. Why there's so many senior managers, I don't know. But if we looked at do the product team have engineers? Product team, it's also kind of flat. I think what we're seeing is that we kind of designed it this way, that there's an equal chance of pulling those different things. Cool. And we can get a bit of like a quick high level view of this. Great. Great. So does this look like a company? I'm not really sure. It's hard to say because we're not seeing any of the reporting structure piece that we'd look at before. We're not seeing really like how these teams are grouped together. We can definitely spend lots of time here and try to think of smart ways to slice and dice the data and look at it flat here and try to make intuitions about whether this is representative of a real company. But I think it's better to look at it in a graph. That's why we're here. Okay, so we can actually make graphs now. And if you're wondering, there's another library that's great for this. It does not make fake data like this. Instead, it makes synthetic data from real data. So the idea is it's not just GAN based, but the idea is that it'll train a model on your real data, and then it will generate data that has none of the sensitive natures of the original data. It is unique and new data. but it retains the statistical features of the old data. And so this is a great option. And Y-data and synthetic is one of the options that I've used before and has worked great. But you can do this yourself if you really want to like train GANs or work with a couple different models to do that. It's an option. Yeah, so a cool additional piece to do if you're following along is like you could check out synthetic data and like take the data we already generated here and then run that through the synthetic data and see if it's kind of similar-ish looking, but with like new names for everybody, new team names. Depending on how much you put into it in terms of like what data to change, it'll be quite interesting. Great. Okay, so now we have data. We have real people, well, real fake people data, and we think it looks pretty good. Okay, so now we can jump to the next section of this. Perfect. So let's get this into a network and visualize it. So first off, we're going to be using NetworkX. It's a great library for creating, manipulating, generally studying, and implementing more complex graph analyses. In Python, it's in memory and it's fast. So sometimes some places this will break is when you have very, very large networks. Typically, in my experience, it's worked for pretty sizable things. Where I see more breaks happening is on the visualization side. Like visualization libraries struggle to put tens or hundreds of thousands of dots on the screen, but like the network is fine putting tens or hundreds of thousands of nodes into memory. That's fine. So typically, though, there's a couple approaches where you shard or use other libraries that'll do that, break your compute across multiple nodes, compute nodes rather. But that's pretty typical of anything that's starting to break from being the in-memory approach. Awesome. So NetworkX, we can create a graph. It is very easy to add nodes to a graph. There's a method add node. We can give the node, it needs to have like a unique identifier here. I think maybe this will be helpful to pull up. So here we can the add node takes a unique identifier, and we refer to it by that. That's its ID. We can also assign other attributes to the node as we make them. So we can say add a node me. It's a type person, and now person is going to be an attribute, or type is going to be an attribute with the value being person. And we can pass in really any objects to it. It'll complain later if things aren't JSON serializable if you try to do other operations with it. But mostly moving the graph into other libraries to do things like visualization, but just something to consider. But yeah, we can also put in a list of values. So here we have languages and it's list, but one element is Python. Great. So I have my graph, I have me in it. We can also add things from iterables. So here, this is a table of tuples, and we're adding in you, and we can specify, instead of being keyword args, we can put in just a dictionary to map it in. And here we're saying languages Python Scala, Python JavaScript. Cool. And both of them we're labeling as type person. So we can add an iterable and populate the graph, and also add attributes to all of them as they're added in. Fantastic. Don't add it too many times. Cool. We can look at the nodes. If we just call nodes, we can look at the node IDs. So that's great. We can also pass in data. And if we say data equals true, it'll give us back that whole object. It took us a while to get here, but now we are looking at this underlying structure represented as a dictionary here. So you can see, here is that node me that I created. And it does really just look like a Python object represented here under the hood. This is a little dictionary in the representation. Great. So all that information is in there. And what's neat about just this accessing and setting piece of network graphs is that it's easy for us to pull out just the pieces that we need, as well as to iterate over them. So it's going to make some of the tasks later on a lot simpler. So here, for example, I can just see everybody's programming languages. Similarly, I could swap this out and say everybody's type, I guess, but that's all the information we put in here. So we have programming languages, and this is like a node data view. What's neat about it is it's iterable as well. So I don't know, do X for X in this. Yeah, so then we can pull out little things, including we could just like go over the values for things. Or pull them out as like little dictionaries and a mapping. Great. So what do we do next? We have nodes. We also need edges. So now we can connect different nodes based on their IDs and then label them. We can also add additional attributes like anything equals 1. Like we can add these things in. So here I'm adding I added too many there, but I added edges from me to you, and the label, this like the type of edge this is friends, which is really nice. And then you and them are also connected by friends, so that's great. We can do a graph-based math here, and so there's a whole, I mean, we're not going to do much of it in this tutorial because we're focusing on the visualization side, but there's a whole wealth of things you can do with graphs that are in the documentation, including things like neighborhood detection or finding influential nodes in the graph. So like things that are most connected, but also things that can be important while not being most connected. So there's some algorithms to do that. They're very popular in social network graph analysis, which is kind of what we're doing and would be a useful thing in this, but we're just focused on the visualization side. Great. So what's one of these things? What's the shortest path from me to them? And it gives it's like me, you, them. We go through you to get to them. You know, we value you, but you're also connected to them and we're interested in them. And we can print all those out as well, all the different interconnections between things. So it's like me and you are connected along friends. You and me are connected, right? Them and you are connected. But me and them are not connected, right? We're not adjacent directly. Great. So network X itself has a visualization function. So we can just draw this and we could end here, but I think we can do better. So here network X is using matplotlib under the hood. It's taking all of the nodes that we have, the edges, and it's generating positions for them. So it does that using some like different layouts. If you're interested, like one is a spring layout, and I can just generate this, and it gives me an array of XY coordinates, and that's what's being plotted right now. It's doing the same for the edges, and it's doing this physics solver in the backend that we talked about before. Great. So let's actually try this with our data. Let's plug it in and take a look at it. So here I'm just running that old notebook, and it's going to go through and print out all the stuff that it printed out before because I was a little lazy. And now we should be up to speed with all the functions we created in the last one. If it gets janky, that's why. Definitely that's why. Okay, now we're ready to populate our network graph. So we need to take the data from that data frame that we created at the end of the last piece, or from the list of those people, person, objects, and we need to push those into the graph. Okay. So I'm a big fan of this more itertools library. It implements a lot of the recipes from the itertools built-in library, and it makes these like really common things you might be using more than you think easier and easier to do. For example, we'll take the first n items of an iterable as a list. Useful. Instead of using like some slicing and then like colon n. I mean, it's simple, but it works on iterable objects as well, like generators as well. Cool. So we create our graph. It's empty. And then we're going to add nodes into it. We can use that add nodes from iterable. And in this case, we're going from our data frame. We're making it into a dictionary, make it easier to iterate over. We could have done this part differently. We're looping through it, and we're pulling out the object type that we want for the graph, which is we want to have an ID followed by the attribute. So here we're using the person's name as the ID, and then we're using that whole node representation, which is like a big dictionary, as the person. We're also setting some more attributes on this for everyone. So we're setting person equals true, which seems useful if we're going to add different kinds of attributes in the future. We're also setting type equals person, because whoever made this tutorial got mixed up halfway through and started using type instead of the person Boolean, and that person was me. Great. And finally, we can take 3 nodes from this and just print them out. Great. So here, we can see a couple people. So who are these people? We have James Roberts. They're a person. That's great. They have a name, a hire date, a status, right? They know some languages. This is the data we had before, and now it's into our graph. That's what we're taking away from this. So now we have all those nodes. Excuse me. And probably we can visualize it. So we have that great draw function. It just works, right? And we can print it. So this is it. These are our nodes. We could probably try it with the names too. But most notably, well, that's not really helpful, but most notably, we don't have the edges. Nothing's connected. It's also just hard to see any differentiation between people. I mean, having all the names clumped together doesn't really help, but something we can do inside of Network X's draw is we can add some coloring to the different nodes. So let's add some color. So let's try to color them by team and then see how the different teams line up. So here we were using doubly before, and so I'm going to just take one of their color palettes. So there's some like great color palettes inside of it, and it's just a list of different colors. This one is meant for qualitative analysis, so they're generally used for categorically different things, and so the colors are distinctly different in color. If you're picking a different color scale, just keep that in mind. If you pick something like diverging or there's a couple different names of things, but things like that are meant to be like, if you think of like heat maps or like different gradients of a single color, it makes it really hard to differentiate. I mean, even using colors to differentiate is a little bit tricky, but it's like one of the dimensions we have access to here. Great. So here we can take that list of colors and we can map it against the unique team values from our data frame, and we can get a mapping from the team to a color. So basically we want to go in and color those nodes with this. Network X doesn't like RGB though. It wants to have a hex value. So we can do some math that definitely came from ChatGPT to convert these into hex codes using some super F-string magic. Great. Now we have a function to generate that. And lo and behold, it appears as if we have different nodes with different colors from different teams, right? That's great. We do like that. Cool. This still doesn't very much make sense. We don't have the key thing of our graph here, which is the edges connecting them together. So let's add those in. Let's add those in. Great. So this is lots of ways to do this, right? We need to generate some iterable here that's going to connect each of our different nodes to the other node based on one of the attributes in the data set. So we can make use here of some of the pieces that we highlighted before and how graphs work. If we look at our graph nodes and just look at the manager attribute, this is actually giving us, if you look at it, it's like a dictionary. I mean, it's a mapping here from a node to the manager. And this is exactly what we need in order to know, like, we want to connect this node to this node. So fantastically, this is giving it to us. I mean, it's not free, but it's C, so it's basically free. Lovely. So that's going to be our iterable, just that's itself. We can add edges from that iterable. If you're thinking like, oh, why not just why manager? Why not other things too? That's what we're going to do. And we'll do the same great thing here where we add a manager as label and manager also true. Great. And hopefully I only ran that once. And when we draw it, it should look a little more like a real thing. And we should be a little bit excited about this, although it is still hard to read them. There's no legend, which is fine. But what we're seeing now is some structures start to form in the physical space of the visualization. So whatever the yellow was, this is like all one team. So kind of strangely, it looks like two people from the yellow team report in to one to the other, and then I mean it's kind of hard, right? But maybe one directly into the CEO. But it looks like teams have their own sub-reporting structure, and this is what we defined before. We said that teams should all report. Everyone's manager should be on their team, except for the team lead who reports to the CEO. So it appears as if this is working. Right. And sorry, I thought about this for 8 more seconds. And in this case, these two yellow people are probably they're of equal level. The two like this fella and the one at the top of the other big bunch of yellow. And that's great. So this looks vaguely like what a company could look like, and we're on the right track. So structurally, we're okay. But we want to analyze more about what the values are inside the attributes. So we want to be able to interactively learn more about this. Oh, great. So there's a couple of ways we can do that. So there are other visualization libraries in Python that allow us to interact with data. One such option is Plotly. So this wraps a JavaScript library, similar to how like Bokeh or Altair or other, yeah, I'm blanking on the others, but they have similar interfaces and we can generate nice interactive graphs. So here's some helper functions. Basically what we want to be able to do is dynamically generate a scatter plot. So we want to draw all the nodes of our graph out as points, right? We want to be able to color those points or size those points in a similar way that you would with a normal scatter plot. In Plotly, it follows a little bit the grammar of graphics approach to plotting. And so basically that means that when we're saying plot this, we say, we can pass in different arguments to say, to control how it visualizes itself based on the actual attributes in the data. So you typically you do this like color the points based on the value in this column, or like make the size of the points the value in this column, things like that. Great. So what did I say we're doing here? The bulk of the work here is we're making a scatter plot. We've generated X and Y coordinates for the points based on a layout that we've generated as well. So we saw the layout before. This is going to give us X, Y coordinates. We're setting that as the X, Y for the plots, for the points. Then we're going to update that with a couple different, I don't know, fun layout things. I think contextual help is getting mad at me here. Great. Once we have the nodes for the graph, which is going to be a figure here, we're going to add the edges. It's optional in this, so there's like a flag to turn it on and off. Drawing all of the edges is a little bit, or rendering all of the edges is computationally expensive, and you might have to wait many seconds for it to render, which is a little annoying. But then we're just doing that same thing where we're going through the list of the edges and we're connecting them if they need to be connected. Great. Cool. So now we can take a look at that same layout of data, and we can hover over and get more information about the points. So like here we saw these purple points. They should be colored by their team. And so we can see, like, digging into this, this is the DevOps team. They have various different ranks based on their, yeah, let's do this with the edges equals true. So we can go and explore a bit and do more of our like high level check here to see, like, does this make sense as a graph? And who are these purple people? Like, they appear to be not the DevOps team. And so, oh, sorry, we colored this by the country they're in. So purple people are in Ireland. Great. And so different teams, but the teams we expect. Also, the reporting structure seems to have people closer to the center. Okay, yeah, here it is. So we have the CEO in the center. And then, for example, here, someone that reports into them is, what is their job here? They're a manager, and then folks, they have a manager reporting to them, and then engineers, senior engineers reporting to them. So this follows what we wanted to kind of get. And now we have a little bit more ability to interact with the plot. We could, I don't know, like really zoom in or something if we wanted to, as well as like highlight different pieces. So we've taken that structure, we've boiled it down into something that most plotting libraries understand, which is XY coordinates. And then we've been able to leverage this interactiveness of the Plotly library. But there's other ways to do this. Oops, I hit it again. So there's some libraries that are specialized for doing visualization of network graphs. One such is PyViz, which wraps the Viz library, JavaScript library. So here we can actually just pass in our graph directly, and we can visualize the points. So here, if we're a bit smart about what the attribute names are, it'll visualize and let us interact with this. There's no hovering capability except for like a single term here. But it does allow us to do the thing that maybe a lot of people have come here today for, which is grab nodes and drag them around, which is pretty exciting. So if this is why you're here, this is the notebook you want to open and drag stuff around. So this is great. As a kind of note here, the library takes a little while to load once you create the, once you tell it to like render the document. It is doing, in this case, we do not pass in XY coordinates. So this is not a static plot. So complaint number one about doing this with Plotly, all of these points are static, right? They are where we plotted them. Depending on how you do it as well, like you could maybe complain that there's some overlapping to these points based on the zoom level. Like you could complain about that. But in this case, it's actually doing the physics solving live. And when I move points around it, it continues to do physics solving. You'll see like I'm like pushing these nodes away. And so this will break down if you add thousands and thousands of nodes in a lot faster than something where we've like pre-computed it and then don't allow it to change. Okay. There's a couple magic values for attributes that will cause the library to plot differently. So one is group. This will control how coloring is happening of the points. I believe we can also specify what the colors are for the different groups separately. Title is what the hover text is. So that's when I actually hover over. Here in this case, it appears as if, I mean, maybe confusingly, we already had an attribute called title and it was like job title. And now because it was called title, it's being used for the title, which, you know, like very clever of the creator of this to conflate all of these ideas together. And not the creator of the library, me, just to be clear. Okay, the label is displayed under the nodes. That's what we're seeing when we zoom in, which is like people's names. It's a little bit tough to see in dark mode, but I don't think it's worth switching around right now. Great. So what we can do here to make this a little more dynamic and a little more grammar graphicsy, like we had going with Plotly, to make this part of our toolkit for exploring graphs, is we can make a copy of our object here, and we can rename title to something else. So then it's not, you know, like sitting on top of that reserved name. And we can do basically the same thing for all of the different attributes we want. So we can make this function and it'll take in a graph, and then we'll give it different values for the different things we want. Like, should there be a legend? We kind of hack that around later. How should the sizes of the nodes be? Like, should that be sized based on an attribute in the node object itself? What the label, title, and color should be. And then we just go in here and set those inside the object itself based on the column name or the attribute name that may or may not be passed in, right? Great. And then we can build the network using Gravis, and then we can show it, right? And then return that. And this is a kind of hack together. There isn't a legend functionality for it. The way it works is we're just going to like make other nodes that are on the graph, and then those nodes will be colored the same way. You'll see in a couple seconds as it, and sorry, this is PyViz, not Gravis. Gravis is next. Great. So now things are colored based on these things. So this is like the team name, I think. Yeah, that's what we put in here. So color is team. We're still labeling by people's titles, but the hover thing is the city that they're in. And then we said make it black background color to make it hard to read. And so now we have colors for things. So this makes it a lot easier to do we're basically getting a lot of what we're doing with Plotly, except for maybe less interactive hovering and hovering support, right? And we don't have that like nice way to filter based on the legend. Maybe things that we'll want to build out later on. So great. Now we can look and see we have folks in Seattle, Toronto, but these are all this pink team, which I think is internal tools. And so they're building internal tools, lots of engineers, senior engineers, VP, and then we see the VP reports into another VP who has their own team of senior engineers, managers, VPs, right? And they report into our CEO, who has a self-referential reporting. I think they report to themselves instead of the board or something. We had to stop somewhere. I'm sorry. Anyways, great. So we have this structure. It vaguely looks like what we're going for here. And we can explore the colors. So we can start to use more dimensionality in how we're plotting. Great. So what's another option here? So this one isn't as fleshed out, but another option with a bit of a newer library is with Graviz. So this actually wraps the same backend as PyViz, which is Viz, but it gives you other options as well. D3 or a three-dimensional plotting library as well. So in theory, we could build this out to have that same sort of, what's it called? That interface, right? We have that nice Python interface, and we could make it so that it's easier to color different things. This one doesn't seem to be finding an equilibrium point so well. It's like still moving, but we can still do our dragging, which we like. And in theory, there's a hover and a way to color these as well. It's just not implemented just right here. But this is a nice, easy, and you'll notice it's a lot quicker to load. But this is another, I guess, quicker to load, but it's not, it's still stuck in the first few iterations of solving, but that's fine. Oh, we hired a dentist as well. That's great. I haven't seen that pop up, and I've done this a number of times. DDS, so, Doctor of Dental Surgery. Fun. So yeah, what other things can we use? Okay, we can also use D3 to visualize it. It just takes in the graph object as an input, which is great. And we'll want to customize that with a lot of different attributes. So if we wanted to make this nice and easy to use, we'll have to figure out how all these things work and map that back into just what we need. Okay, cool. But great, D3 also does a great job of visualizing this, and we get some of that draggy droppy. And the other neat one, which is neat for exploration, but maybe less neat for showing off, is we can also plot this in 3 dimensions. So before, we were losing some of the meaning of the data, perhaps the interpretability of the data, by putting it into 2 dimensions. So we're taking information about the relationships and relative positions in the graph of data, and we're condensing that down into something visual in 2 dimensions. We could also condense that down into something visual in 3 dimensions. And this is what it looks like. So we can drag around to explore this 3-dimensional object. This is really, really interesting for more complicated pieces, especially as we start building out more attributes that we want to include in the graph, right? But it's not fantastic for, well, one, it requires you to actually physically interact with it, as opposed to something which has value just as a static plot that you can look at, right? Like zooming in here is great and like looking at pieces, but there is value to having that already baked in like that. Anyways, I think they go well together, and you can explore and investigate the relationships between people and see, you know, maybe it's a little easier to find the CEO here in the center. But these are an interesting newer library with a couple different options for plotting, depending on what you want to do. Great. Oh yeah, other approaches to this. Probably what we want to do is not hold ourselves to just 2 or 3 dimensions and not only use a physics solver in order to reduce this down. So like common approaches to this is we'd probably want to like take these nodes, put them into a vector space in higher dimension, so not just 2 or 3 dimensions, and then use a dimensionality reduction and visualization algorithm like TSNE in order to take that and put it back into 2 dimensions, but in order to best still represent, excuse me, the relationships between the different nodes. Fantastic. Okay. I want to speed up a bit and sort of zoom through this next piece. Basically, what we left off with is we have our graph nodes. Here they all are spitting out here. But what we don't have is we don't have. Hold on, I think we left some of this. Comment out the piece that takes a long time to run, so we don't have to sit here and wait. In the future. Great. So we have our attributes, right? We remember this. They're connected. We're connecting by the management, but we want to add more of these nodes in. Okay. So we have all the building blocks to do that. Basically, what we want to do is write a little helper function here in order to add nodes based on unique attributes. So this is going to go into our graph. It's going to find all of the unique attributes. And so this is creating, we're going to make a set of all of the unique attributes for a given one. So we say like pick city, we'll get that set of unique cities. And then we go through that set and we add a node for each one. We also flag them, right? So here we're going to add in all of the different cities as their own node with their own flag. Another way to do this that we don't address here is you can, instead of using like a standard graph like we're doing here, you can use a bipartite graph. And so you can store these attributes in like a different context within the graph, as opposed to them being, right now, the only way we're differentiating them is with these flags, like the internal attributes. But if we wanted to, we could store them as a different, like in a different layer of the graph, you can think of it. And that can help us to visualize them later without them like interacting as much in the, or have different rules for how they're visualized. But for this, it does work. And we're going to sort of take them all at the same level. Great. Okay, so we have our helpful function. We can add in the different nodes for languages, for cities, and for time zones. Great. And it's easy for us to use this function in the future to dynamically add just what we want. That's a point we want to get to. Next, we want to add those edges. So this is the same approach we took before. Here, there's another like feature of NetworkX is we can give it a filter criteria and get just like a subset of the nodes in the graph. So that's what the subgraph view does. Let's pull this back up. That's what the subgraph view does here. And this allows us to filter down to just people in the graph. So we want to look at all the people nodes, and then we want to get all of the mappings from the attribute we provide, which is whatever we provide in the function. We want to loop through these, and we want to add edges from the name to that attribute for everyone who has that attribute, right? Great. This is a kind of a generalization of what we were doing before. And it's going to mean that we can say, go back into my graph G that now includes attributes nodes for languages, and make edges to connect all the people who have a language to the node of that language. Great. Fantastic. We can plot that and take a look at it. Basically, all we see here is we should have some new nodes, like there's new nodes for just languages that are scattered around here, along with all the people, and that the people should be connected to them too. Great. I guess we could look at that with like a three-dimensional plot if we were like really feeling excited right now. And this probably won't resolve very well, but so we should be able to like explore and see like people starting to group up into different regions based on like here's PSD, like the time zone, and it's close to Seattle, which is like this is a very good confirmation of our vague intuition about how this works. Like Seattle is in Pacific Standard Time, and so we would think that people, the two nodes themselves aren't connected, right? They're not connected, but everybody who is connected to one of those two nodes is also connected to the other, and so naturally they're being pulled together. And this is really a good indication of like what is happening here. Similarly, right, like in our data set, I think maybe two different cities are both in the same time zones. There's a lot of overlap there. It's not like the most useful metric, but in terms of us building this intuition, I think it's really helpful. Great. So yeah, what else can we do here? We've added in all of these attributes into the graph. We can actually do a lot of graph analysis now without visualizing, right? And so one way to do that is to make an ego graph. It's centered around somebody or one node in the graph, and we can look at all the other points that are within some radius. So the radius itself is like the number of steps. So we can look at anyone who's connected within one step of you, which is in this case, managers, right? Anyone you manage or that manages you. And then the attributes like language, like Python, right? The next step away from that is your manager's manager, right? But it's also anybody who uses the same language as you. So we could use this as a way to look at people who are similar to you. Basically, it would allow you to find people like with the most number of similar connections to you, which is definitely interesting, and it would definitely be a great part of this. The only downside to that and what we're losing is that we don't have the context of like what things are similar. So what we just saw here with PST and Seattle being similar nodes, or like here, yeah, Seattle and PST being similar nodes. Sorry, this is like unruly at best. Is that that they actually aren't necessarily, they're equally far away from you and far away from each other in the graph. They're both connected only through you in this graph and everyone else who shares those things. And so we're losing that context of like natural clusterings that are happening that might have more meaning than just the sort of like naive distanceless approach to things, which is fine. There's other ways to accomplish that as well. If you look at especially the neighborhood section of the NetworkX library, great. Here's another way to do it where we go and make that spring layout, and then we just do like a pretty simple Euclidean distance between all the points, and you find people that are within your area. So this is basically the same approach as plotting it and then drawing a circle and saying like, they're all close to me, right? So we're getting some of that magic from actually plotting it and from the physics. And then we're reaping that. Great. Cool. So yeah, check out some extras if you want to have homework after this, I guess. Perfect. I think this is the old one. Great. So we have all the pieces we want now. Oh, maybe we don't. Come back to the main plot here. Right. So yeah, that's what we were seeing here. We have a way now to visualize and start to look at the neighborhoods that are emerging and similarities between people. So now we have folks like Joy Baker DDS. We have so many dentists now. and Jamie Castro here. They're very close together. Like they're being pulled together by a number of different pieces, by a programming language, by a time zone, right? And by their location. We want to be able to take this, which is a little bit difficult to look at, to be honest, and make it more customizable. So how do we take the visual pleasing piece, but then also make it interactive, but also make it available for someone who might not have the tech skills to use a notebook like this? Because basically what I have to do is come in here and like change. I want to color by a different value. Like instead of it being team, let's make it city, and then run this, and then look at the different pieces and reassess, right? So we can build this out into an interactive application as well. So if we're already using Plotly, which is great, associated with Plotly is another library called Dash. And so what Dash is it's it actually doesn't need to use Plotly at all, but it uses Flask as a web server and generates React code. And it will serve that for you in order to make very potentially complex and pleasing web applications only using Python. So here's a very simple example of how we can make this available for users and make it interactive. So here we can like create our Dash object, import some stuff from Dash. We create a layout, which is the wireframe for the application. So here I'm like, this all comes back to like very weak wrappings, loose wrappings around actual HTML. So it's just Python and HTML. And so here we set, we have like a big div that everything's in. There's a header, it's going to say something. There's a paragraph here with something in it, and there's a button. Buttons are great. We can also define a callback. And so this is the way of adding interactivity to the application. I'll show you it in just a second. And so in the callback, we say when the button and the attribute of button, which is number of clicks, is changing, run this function. And the return from the function should be put into this, which is, in this case, it's this thing, the ID of title. So it's this H1 header on the top of the page. And its children is what's contained within it. So I want to replace its children with the result of this function, right? I'm going to really quickly switch to light theme. I'm sorry for blinding everyone. So yeah, we have this simple app. This is running in an iframe inside of the notebook, but it actually can run as a normal application. Like I mentioned, it's a Flask app. So this is my app, and I can click a button, and it does something, right? Fantastic. This is going to be the cornerstone of everything we need to do to make this app a bit more available. This is a more complicated version, which introduces Bootstrap to prove that it can be a little bit prettier. I'm not going to go through it too much. If you're interested, check it out. I don't know if I have to start. Oh. I forgot to, okay, I'm in order. That seems fine. Great, so now we have a dark theme application. We chose the theme from available themes in Bootstrap. And this is gonna have a couple different inputs. So here we're choosing the number of paragraphs it's generating, and we can choose like a color for the paragraph. Really just meant to be indicative of how to customize these pieces as you're going. The last piece we have to do is we wanna be able to generate our graph for people. So let's load in all that graph project that we have. And if we looked at the like sample app that we want to make, oops, we don't like that. I was hoping it was just going to work the second time. It clearly didn't. Yeah, we don't need to debug this live. That's fine. So there's a couple ways that we can simplify generating the things that we need to generate. Basically, we need something that takes our data, whatever form it's in, and it makes the graph object for us. The graph object should have like this should look familiar. We've kind of been building this up throughout the process, but we're making a graph. We're adding the nodes from all the people in our data frame. So this is taking the data frame, turning it into a graph. Then we need the next step, which is we need to go through each of the attributes that we want to highlight in the graph and only add those in. So this is going to be one of our like drop-down interactive elements when we're building our app out. That's going to let us explore this a little more. So we go through and we add the attributes given in this list, right? So now we can pretty easily call that. And we add the edges and the nodes from them, right? The last piece is we need to take our network X graph that we just have now and put into a format that we can plot with Dash. So Dash has a couple ways to do this, but the most, well-supported way is with another JavaScript library called Cytoscape that does graph visualization. We could actually have used that the whole way as well, but there's no like interactive Python wrapper for it, which is fine. Great. So what we need to do is create elements from it. Luckily enough, Network X provides a function to do that. We can just pass in our graph and it will dump out to us a format that we can pass into Cytoscape. Great. So we do that for the nodes and we do that for the edges. And then we can create our graph and return the edge elements in it, which is going to be just like a big dictionary in the right format for it. We can also play around with Cytoscape allows you to style things based on attributes that are inside of the nodes. So this is how we're doing that same thing with like coloring nodes based on a certain attribute, right? And the way it wants it is with a little like it has its own selector language, which does some like pattern matching based on values that are inside of the nodes or the edges. So here we're saying like all nodes should be light gray with this font size. And then somewhere down here, we're saying like any edge that has the label apps, any node that has the edge that has the label apps should have this label on it. Great. So we can do that and dynamically generate that and style that for our app. And then really the last pieces are just plugging in the drop downs or interactive elements that we already have functions to generate and giving that control to the user. And the app itself is pretty simple. We have our little Cytoscape thing. We have a div. There's a bunch of nonsense that we put in here about having links to different things, but a lot of the key stuff is like in this drop down. And so we define some different drop downs with different options. And then that's going to pump through the app. And then our callbacks themselves, we're just whenever someone changes which attributes they want to visualize, we create the elements for those attributes. And whenever they update the color and the way they want to color, we change the style sheet. And we can run that. And we're happy with that. So if you've sort of like, if you checked it out before, what this is when it's in action is our interactive plot here. We're looking at our data. We can change which values are being rendered as attributes. I can keep removing things and just divide people up in different ways. And potentially this is something that we could give to people who are new and starting. We can customize and build from this point. Awesome. So I know we're basically at the end of time now. Thanks for stopping by. Thanks for following along. If anyone has questions, and we have time for questions, I'm not sure if we do, happy to answer some of them. Happy to do that after time as well.
Hey, sorry, I might have accidentally muted you. Yeah, we probably have time for like a question or two, considering this is the last session of the track. So luckily we can do that. But yeah, we probably got 1 minute left.
Great. I think I'm back.
Yep.
Yeah, there's a couple questions in the Q&A. I can kind of just like rapid fire go through them. Is this how this works? Is there a rough rule of thumb for what network library to use based on the number of nodes and edges? Yeah, so Network X can do anything that fits into memory. You know, your mileage will vary with that, but I use it as a standard for everything getting started. I've never run into a big issue with it. If you're starting to work with massive, massive data with a lot of connectivity and information in it, you'll need an entirely different approach to things. So like you can think of things like another very popular one is Neo4j, right? But you need to use like the enterprise version that has sharding and distributed compute involved. Another approach in the open source world though is like Spark has distributed graph representations as well. So you can use Spark and some distributed libraries like that as well to represent your data if it gets really, really big. Awesome. Yeah, apologies. I didn't see a lot of the questions until now, but some of these might be old. When you're looking at creating flags, does this mean all nodes are of a type node, essentially with a name of the type of the node it is? Or will it actually create a country node? Yeah, so this is referring to like how we're creating those flags on the nodes. They're not necessarily associated, and that's a little bit of the art of like how we set all of this up. It's just adding another attribute to that node, and then later on we can filter by that attribute or treat those nodes differently based on whether or not they have them. So this is just a method that we have in order to keep them separate logically as we're building this out. Good question. Great. Skip to someone different here. Any comments if there is any potential of graph neural nets in solving this problem? 100%, definitely. Way too complicated for us to talk about on top of this with all the other pieces. But yeah, there's lots of ways to solve this specific problem. Another really common way to do this without just visualizing and looking at the data, which is, you know, we're putting a lot in the hands of somebody like, yeah, somebody knowing what they're doing and like using this correctly. But anyways, long story short, a really common way to solve this is to take the graph that we've created because it's powerful and then make a vector representation of it, usually using something like node2vec, which is a library to take these nodes and then cast them into a higher dimensional vector space. And then a lot of the more modern AI ML algorithms actually work in vector spaces already, right? And so you're handing it something that's already in there and you're asking it to do things like build clusters or like find nearest neighbors. And like those algorithms are really a lot easier to execute in that space. So that's kind of like what we're doing visually, like trying to like look for clusters. And you absolutely can do that programmatically and with a number of different methods. Nice. Great. There's a couple more questions I think we answered in the course of going through the notebook, but yeah, thanks again everybody for tuning in and for coming out. One more question popped up, and the question is just thank you. So thank you. Yeah, it's been great.